So the total resistance between the hot fluid and the cold fluid in this heat exchanger is the sum of the three thermal resistances that are in series, and we can, in the case of the heat exchanger, try to express all of this with an overall heat transfer coefficient. So by definition, the total thermal resistance is equal to 1 over UA, with U the overall heat transfer coefficient, and A the heat transfer area between both fluids. And that's a way to put all the different types of heat transfer and thermal resistance into one single coefficient, U, that is homogeneous to a convective heat transfer coefficient. Here, because we consider that the inner and outer surface are equivalent, we only have one U. We don't have UI and UO because we consider only one single heat transfer area between the three. So therefore, with the expression we had written before about the three different thermal resistances, we can express U, the overall heat transfer coefficient, as a function of three terms here, one related to inner convection, one related to conduction, and one to outer convection. Here, for the inner convection, we have a flow inside tubes. That's pretty easy from a thermal point of view because we have easy correlations for convective heat transfer in a pipe. On the outer side, it's a lot more complicated because here we have a geometry that is specific to this heat exchanger. So we'll do one big assumption in this exercise. We'll consider that the inner and outer heat transfer coefficients are equivalent. And this could be more or less true if the cross-section of the flow on the outer side is more or less the same than what we have inside. So, in order to calculate the overall heat transfer coefficient, then we know everything except the convective heat transfer coefficient, and we will calculate this HI, the inner convective heat transfer coefficient. In order to do this, we will use thermal correlation, and to choose which correlation is fine, we need to first calculate the Reynolds number. In order to calculate the Reynolds number, we need the mean velocity of the flow in one cross-section inside the pipe. And so first we can calculate the cross-section. We know the diameter of the pipe, so the cross-section can be easily calculated, and we find about 7 at this minus 4 square meter for the cross-section inside one pipe. Okay. Then concerning the velocity, the total mass flow rate is divided into the 100 tubes when it enters the heat exchanger, and then everything is probably collected to one single pipe in order to go outside. So if we want to calculate the velocity inside one tube, we need to take into account only the mass flow rate that is going through one tube. So then we can divide this mass flow rate by the number of tubes, and we get the mass flow rate flowing through one single pipe. And in order to get the mean velocity, we can divide this mass flow rate by the cross-section and by the density of the air, and we get 10.25 meter per second for the mean velocity in one cross-section of one pipe of this heat exchanger. Once we have this, we can easily calculate the inner Reynolds number, and here the hydraulic diameter is just the normal diameter of the pipe, And using the thermophysical properties that are provided in the exercise, we get Reynolds number a bit over 22,000. This is far above the transition between laminar and turbulent flow, so we can consider here that the flow is fully turbulent. For this reason, we can use the very well-known Colburn correlation that relates the Nusselt number here with the Reynolds at the power 0.8 and with the Planck number at the power 1/3. And calculating the Nusselt coefficient, we find 61.8. Using this Nusselt number, we can now calculate the inner convective heat transfer coefficient using here the conductivity. So be careful here, we are speaking about heat transfer inside the air that is flowing inside the pipe. So don't mix up with the conductivity. Here it's the conductivity of the air that needs to be taken into account. And here again we have the hydraulic diameter, that is the pipe diameter. And we find an inner convective heat transfer coefficient of 50.7 watts per square meter Kelvin. So that's it for the inner heat transfer coefficient, and now we can calculate the overall heat transfer coefficient that takes all of this into account.